Hi, in this tutorial I'll show different features of Gaussview. Then I'll show how to build this molecule and how to optimize the structure using DFT method. So firstly I'll create 1,2-difluoroethane. So go to this element fragment section and choose carbon, then this carbon tetrahedral fragment, and left click on this window. Okay, so this is a methane molecule. Now I want to substitute this hydrogen with methyl group, so click on this hydrogen. So this is a ethene molecule. Now I have to substitute these hydrogens with fluorine. Okay, so click on fluorine and click on these hydrogens. So this is 1,2-difluoroethane. Okay, now I'll show how can we change different bond lengths, bond angles and torsion angles. Okay, so click on this option to change bond length. So now we have to click on two atoms. So we can see that the carbon-carbon bond length is around 1.54 angstrom. So we can also change this bond length. Okay, so in this way we can change the bond length. We can also fix one atom and change the bond length. Now we can also change the bond type. So here I am creating a double bond, and now we can reduce the bond length. Okay, now I'll show how can we change bond angle. So click on three atoms. Okay, so we can see that this bond angle is around 109.47 degree. Okay, so now to change bond angle we can fix atom 1 and 2 and rotate third atom. Okay, so in this way we can change the bond angle. Now I'll show how can we change different torsion angles. So click on this option, and suppose we want to change this torsion angle. So click on the four atoms, 1, 2, 3 and 4. So we can see that the torsion angle is 180 degree here. So suppose we change it to 60 degree. Okay, so here we can see that the fluoride groups are in Gauss conformation. Okay, now we can also select one fragment from this molecule. So choose suppose I want to select this fragment. Okay, so choose these atoms. Now copy this fragment in the clipboard. Okay, so press Ctrl+C and we can see this fragment has been copied. Now suppose I want to substitute this group in this position. Okay, so click on this hydrogen. So we can see that this group has been substituted. Now clean this molecule. So this is our molecule. Now we can save this file as PDB. So we can save this file as PDB. Suppose we are giving a name fluoro. Okay, and now our file has been saved. Now we'll create this molecule. Okay, so firstly go to this ring fragment section and choose naphthalene ring. So left click on this window. Now we have to add keto group in this position. Okay, so go to R group fragment section and choose formal and click on this carbon atom. Now we have to replace this carbon with nitrogen. So go to element fragment section and choose nitrogen, then this fragment. Now click on this carbon. Now we have to clean this molecule. Now our quinolone moiety has been created, and all the bond lengths and bond angles have been modified according to the elements. Okay. Now we have to attach methyl group in this position. So go to element fragment section and choose carbon, then this one, and click on this hydrogen. Now we have to attach glycine residue in this position. So go to biological fragment section, and this is the glycine residue. So we have to attach nitrogen in this position. So click on this nitrogen and click on this hydrogen. So this glycine residue has been added. Now we have to attach alanine moiety, alanine residue in this position. So go to this section and choose alanine. Now we have to attach this nitrogen in this position. So click on here and click here. Now this peptide bond has been created in this position. Okay, and finally we have to add the pyridine ring. So go to ring fragment section and choose pyridine. Now we have to add substitute this group in this position. Okay, so click on this carbon and click here. So now our molecule has been built. Now we'll optimize the structure using DFT method. So go to calculation setup and change the job type to optimization. Now in the method tab, choose DFT and B3 functional. Now here we'll use a 631G basis set. So this is a standard basis set. Now for diffuse function we'll use double plus. So it will impose a diffuse S function on hydrogen and one set of diffuse S and P functions on heavy atoms. So for polarization functions we'll use D and P. So P functions will be added on hydrogen atoms and D functions on heavy atoms. So the net charge of this molecule is 0 and the spin state is singlet. Now we can give a job title. Suppose the title is optimization. Now we can also increase the speed of this job. Okay, so we can increase the memory limit. So here we will assign 1 GB RAM, and we can also increase the processors. So here we will use 4 processors. Now we can also change the name of the checkpoint file, but here we will use only the default name. And this is our input file. Okay, now we will submit the job. So before that we have to give a file name. So .gjf is the extension of this file, and now we can save and submit the job. Now the optimization process is completed, and this is the log file. Okay, now we can also view the results in result summary. So this is the energy of this molecule in Hartree unit, and this is the dipole moment. Okay, now we can also save this file in PDB format. Save it PDF format, and we can also do further calculations with this log file, like coordinate scan, then frequency calculation, and NBO analysis. Okay, so I hope this video is quite helpful for the beginners, and thank you for watching.